Hi everyone, thanks for coming. Today I'm going to introduce my work SW-VAE, a weakly supervised neuron disentangled representation by a latent factor swapping. My name is Jiageng. First, I will introduce some background about what is disentangled representation learning. Then I will discuss some limitations shown by previous work that why unsupervised learning work does not work. So first, I will give some brief introduction about what is disentanglement representation learning. A latent representation, Z, which can be called disentangled, if for this latent representation, we only change one given dimensions on this latent representation. There is only there is only one underlying factors shown in the data that will change correspondingly. As you can see the figures below, we only changing the first dimensions value, which change from 0 to 2. So after we changing these factors, in the image, there is only the shape of the figures will change, but the locations, x, and y locations and the size of the shape will not change. Because of this definition, we can formally write this definition as an equation at the bottom of this slide, which is the joint distribution of the latent space is equals to the product of the products of the distribution of every latent factors. So for previously, a lot of work focused on unsupervised learning for disentangled representation, but as pointed out by the work challenge common assumptions in the unsupervised learning of disentangled representation. This work pointed out that if we're using the unsupervised learning method, because for unsupervised learning method, we only get access to the input image, which is X, so we don't have any supervision signal from the latent space. Because of that, the unsupervised learning method cannot distinguish two models which has the same joint distribution on X but has different distribution on Z. Because of that, if we want to achieve the disentangled representation learning, we need to introduce supervision signal. And the bottom one is the VAE method used to train the disentangled beta VAE method to train the disentangled representation learning. Other methods like the factor VAE, DIP VAE, and beta TC VAE is actually doing some modifications on the KL divergence at KL divergence term showing in the loss function of VAE, but all those methods are limited to be unsupervised, which has to be improved by this previous work that they cannot actually achieve the disentangled representation learning. So because of that, to solve this problem, we have to introduce supervision signal. In this work, we are inspired by the fact that because the disentangled representation learning, as I introduced before, is defined that if one changes on latent factors will change corresponding only one generative factors showing in the image, as the image showing on the right upper corner. So ideally, if we had a very good encoder, for the pair of images, let's assume that right now we only have one factors that are different. If we have the good disentangled representation learning encoders, after the encoder, there will only be one latent factor that will be different from the corresponding locations, which is showing in the red colors here. So we can actually introduce the supervision signal by using a pair of images. Because we are not actually using the ground truth generative factor, so this method is a weakly supervised method. Formally, the equation can be right as the left corner, which is the if J is not in the differences, df means the differences of the latent space, then the distribution of that conditional distribution is actually equals to another corresponding latent factors on the same dimensions conditional distribution. Otherwise, it should be different. Because of that, inspired by these ideas, we design our models like this. So we are actually using the pair. We are actually using a pair of images, which first is a circle and another one from this pair. It's a heart image. So after the encoder, we have the latent factors. Then we detect which latent factors is the most distinct from the other one. Then we exchange all other factors except the most different latent factors, and then we can construct the new latent factors. The new latent factors is then taken as a new input of the decoder to decode the new reconstructions. So the model's architecture can be shown here, and all encoders are share the same parameters, and all the decoders share the same parameters. A more detailed explanation is that for the path over here. So this is actually the regular VAE path. So it's the same for here. This is regular VAE path. You cannot introduce any supervision signals here, but the pair of images are encoded after the encoder. We can have two latent factors. The two latent factors are detected, and to choose which latent factors are most different from the other ones. Then we swap except the most different one. We can have the new latent factors by swapping all factors except the most different one. As you can see here, the most different one is the first one. So we don't swap them, but we swap other part. Then in this cases, we generate new latent factors, and then after the decoder, it should perform some new reconstructions. So ideally, if the encoders can actually learn a good disentangled representation after the swap, the new reconstruction should be close to the original reconstruction, because we do not swap the most distinct one, the other latent factor should be stay the same with the original one. So by comparing the new reconstruction with the original reconstructions, the supervision signal is introduced, and we can use that to learn the good disentangled representation. Good disentangled representation. So the first thing is that how we can detect the distinct generative factors. So good news is that because we are using a VAE architecture, and in VAE we are actually using the reparameter trick to form our latent factors, which we can view the latent factors as a distribution of the it's a multivariate Gaussian distribution, and because of that we can directly calculate the KL divergence between two corresponding dimension of the two latent representation by showing below. This is very easy to deduce. It's just two normal distributions, KL divergence. The larger KL divergence means that they are more different. They are more different from each other. By using that, we can actually detect which one factor is different from the other one. And then after we detect which one is most different from the other one, we can actually swap the other factor except the one we detected. We accept the factors we find out is the most different from the other one. After we generate the new latent factors, we call it ZL hat and ZM hat. We can take that as a new input of the decoder as shown here. So we can generate two new decoders, X hat reconstruction L and X hat reconstruction N. as I introduced before, because we only swap the factors that is the same with another pairs in the image. So, and also we keep the distinct Latent factor that is not swapped. So ideally, the new reconstruction XL should be close to the original reconstruction, X reconstruction L, and also it's the same in another pairs, which is X head reconstruction M should be equals or at least similar to X reconstruction M. And that can be taken as objective functions of our models. So the final objective functions can be written as here. Besides the regular VAE training, which is showing here, we add two regularization, which we compare the new reconstruction after the swap with original reconstructions. The LG is any proper distance functions. For example, we use MSE loss and binary cross entropy loss. Both that can be okay, and both functions result similar result. So, but during training, during training, especially at the beginning of the training, it's hard to the model is not well trained, so it's hard to find out. After the swap, it's hard to generate the meaningful result. So we propose two training strategies to solve this problem. The first one is the ISF, which increase number of latent factor to swap as training progress. As you can see, during the warm-up pages, we only swap the most confident, which is the minimum KL divergence. But as training goes on, we increase the number of factors we increase number of factors swapping to generate new latent factors. In the end, which will reach is swap latent factors except the most distinct, most different latent factors. Another strategy we are going to use is that we increase the distinct generative factor in the dataset. We call it IGF, increase the number of distinct generative factors used to produce image pairs as a warm-up. So we only choose a pair that there's only one factors are different. So as the training goes on, we will increase the number of different generative factors in those pairs of images. So after I introduce my method, I will going to show you some experiment result. The dataset we are using is actually some common dataset used in disentangled representation learning areas. The first is Dispirit, which is a 2D containing the 2D shapes that has on the different locations. Another one is a 3D shape, which is the 3D models have different generative factors. The last one is called MPS3D. MPS3D contain three different datasets: MP3D real, toy, and realistic. The toy and realistic dataset are actually synthetic datasets generated by different 3D model software, but MPS3D real is actually taken photos from the real world. So those three datasets can be viewed as three different levels of the realism. The MPS3D is is the most challenging dataset used for to evaluate disentangled representation learning. For the metrics, there are many metrics proposed to evaluate the performance of the models. MIG, SAP, IRS, FAE, and DCI. There are many work discussed which one is better, but to make the fair comparison, so we decided to include all of them. And but from previous work, the MIG mutual information gap and DCI disentanglement method will be the most reliable one, because both of them are using actually a neural network to estimate the performance. Also, they can be calculated very efficiently. So first, I will going to show the result on the disparate. The red one, all of this matrix is higher the better. The red one, red value showing the best one, and the bold black showing the second best. As you can see here, our method actually showing the very good result comparing to previous method. The DSD method is actually a semi-supervised learning method, so it's actually using some supervision signals to train, using some ground truths to train the model. Another result I can show is it's a result on MPI 3 dataset or 3 dataset. As you can see from the tables that our models can achieve very good result comparing to all other weakly and semi-supervised learning method. Those two tables are actually only containing the mean value of those metrics. For more detailed result about the variance, we plot the box plot in our papers. You can check it there. The last one is the application study of our paper. So first, we want to check the sensitivity about the new regularization, which is comparing the new reconstruction with the original reconstruction, how our model is sensitive to that. So this is the result as we can see when we increase the gamma, which is hyperparameters, to the new regularizations, the all of those matrix performance will first increase and then stays the constants. So this shows that this is at the beginning the model is very sensitive for the regularization because you are when you make the gammas, which is hyperparameters, larger than 0, you are actually introduce the supervision signal, which is needed to train the model to learn the good disentangled representation. Another one is that we want to show that the performance when we're using the strategies we mentioned before, and those results are tested on disparate dataset. By using both methods, the models can perform the best one, and by only using the IGF, the models can have good, much significant better performance than if we don't using any of them. So this shows that the necessity of using the strategies to help the model to training more smoothly. The end of that is some reference, and that is all for my work. Thanks for watching. If you have any question, you can contact me. Thank you again.